what we learned last time. So what we learned last time was, it's what happens when we have a localized kind of nano metallic structure. So if you have a metallic nanoparticle, what would be the resonance conditions, and then at what frequency this resonance would happen. And because we are talking about a very, very small particle, we can apply what is called electrostatic approximation. And then within that electrostatic approximation, what we can get for the polarizability of the particle is this equation, like alpha, the polarizability, is 3 times the volume of the particle times epsilon m minus epsilon d divided by epsilon m plus 2 epsilon d. And unlike dielectric particles, metallic particles have epsilon of negative, right? So here the denominator can be 0, can vanish. So the polarizability can diverge if there's no loss. And if there's a loss, of course, it has some finite maximum value, right? And then we try to compare and give some hand-wavy argument of the resonance conditions for the bulk, surface, and particle localized surface plasmon case. And we also talked about the scattering and absorption cross-section of the nanoparticles. And here I want to give you some more information about like what's going to happen if we kind of move away from the ideal situation. So we first consider about non-spherical particles. Like so far, we've talked about like perfect spheres. But what happens if our particle becomes squeezed like this? Okay. Then, of course, like let's imagine that we have a situation that our particle have the same size along the vertical direction, but it's kind of elongated into this horizontal direction. Then what happens is that the resonance, when the electromagnetic incident electromagnetic wave is polarized vertically like this, then the resonance remains at the same position. Okay, so the vertical resonance doesn't affect it too much. But if the incident electromagnetic wave is polarized in this way, then it actually its resonance condition changes by a lot, and because basically it requires charges to move a longer distance, much longer distance, and because of that, if you elongate the particle, your resonance becomes redshifted. Okay, so this is kind of a simple mechanism, like what's going to change if you have a non-spherical particle. And then this is a specific equation to describe it, but I don't think it's too important. Okay, now we want to talk about the validity of quasi-static approximation. So we said that our particle is small enough that we can ignore the phase advance of light within this small size, so the size of the particle, so that we can apply a quasi-static approximation, basically changing your electromagnetic wave equation into something more like electrostatic equation. This is like quasi-static approximation, and by doing so, your solutions becomes extremely simple. But this assumption will be not valid if your particle size becomes large, right? So that you cannot ignore the phase advance of electromagnetic wave within the length scale of the particle. So and then you kind of enter into that regime when your particle becomes larger than 100 nanometers. Okay. So what should we do then? Well, if you want to get a rigorous solution, rigorous mathematical solution, you can still apply the Mie theory that I mentioned like earlier in to describe dielectric nanoparticles. Like you expand it into a spherical Bessel functions, and then you can apply the boundary conditions to get the infinite series. That is exact solution. So there's no problem doing that, but it's kind of complicated, right? So instead of doing that, there's a simple way to get a corrected equation for the polarizability. And if you remember, polarizability of sphere in quasi-static limit, it's 3 times the volume, and epsilon m, epsilon d, epsilon m plus 2 epsilon d, which is just this term, right? And then if you take into account the size effect, so here we introduce the factor x, which is a normalized size of a particle. So the circumference of the particle is normalized by the wavelength of light. So this x tells you the size of the particle with respect to the wavelengths of light. So if x is large, then these terms becomes larger. So these are higher order terms basically, which depends on the size of the particle. And then what it tells is that I don't want to go into detail, but I'm just telling you, the meaning of these two terms basically. So the first order, the lowest order correction is that if you go to a bigger particle, then it takes plasmons to kind of oscillate this particle, like kind of circle around this particle one round, because the circumference becomes much longer than before. So it takes plasmons to more time to basically circling around, and which leads to a redshift due to the retardation. Okay, this is called the retardation effect. And then the another correction, if you can see here, have a I term. Okay, so I is, of course, this is an imaginary part, and adding imaginary part is basically means adding the loss to the system, right? Why this loss appears? Because now if the particle becomes large, then you should take into account that this particle loses its energy due to the radiative decay. So what I mean by radiative decay is that as this particle plasmon oscillates, it actually emits radiation into the free space, and that's how your particle loses its energy into the free space. So that term becomes significantly larger when your particle size becomes larger, so that you have to take into account that effect. So these are the correction factors. Okay, but still, I mean, these are not too important. I'm just giving you this information just to give you the full picture of everything. Okay, but the specific details here are not that important. And then I don't want to give you any derivation why these terms have this specific form, such as like epsilon m divided by 10 plus epsilon d. These are not that important, I would say. So if you actually look at the plasmon resonance, like a scattering cross section as a function of wavelengths of a rare gold particles, of size of 50 to 100 nanometers, you can see as the particle size increases, your resonance position actually goes to the longer wavelengths, right? So it redshifts, and at the same time, its scattering cross-section increases by a lot. And then the cross-section increase is basically due to this, this relation. The cross-section is proportional to the alpha squared, and alpha is proportional to the volume. Okay, and here the same, it's the same plot. The position of the resonance goes to the longer wavelengths as the diameter of the particle becomes larger. So it's just a redshift as your particle becomes large. And then I said that the particle loses energy in two ways. And then originally we only took into account the effect of non-radiative energy loss. So what I mean by non-radiative energy loss is that electrons, so basically what's happening here is that electrons in the particle are oscillating back and forth, right? That's what plasmon is. And then as the electron oscillates back and forth, it scatters with other particles like phonons or impurities or many other electronic transitions you can consider. And then that's how your electron loses its energy. And that energy loss is called non-radiative energy loss, because in this energy loss path, there's no light radiation occurs. So in that sense, it's non-radiative energy loss, or sometimes it's dissipative energy loss. Okay, and then another way of losing, the other way of losing energy is through a radiative pathway. So as the electron and the charges are moving back and forth, it also creates electromagnetic radiation. And then of course, electromagnetic radiation carries energy, so that there's the energy loss due to the radiative channel. And then like when we say loss here, like in our previous discussion, like say here, we put epsilon m is equal to 1 minus omega p squared divided by omega squared plus I gamma omega. Here, this gamma is due to the non-radiative energy loss. It's just a material loss, right? The electron energy loss due to the scattering with other particles. And here, I times this term is due to the energy loss due to radiative decay channel, like losing its energy as a form of electromagnetic radiation. Right, so these are two different damping pathways of plasmonic nanoparticles. And now, if you reach down to extremely small particles, like particle sizes smaller than 10 nanometers, what happens is that there's a here in this regime, a particle size itself becomes smaller than electron mean free path. So what electron mean free path means is that electrons are moving around inside the metal, and then, as I said, it undergoes multiple scattering event, right? Scattering event due to the impurities and other particles like phonons, and then the average distance between consecutive scattering event is called mean free path. Okay, and then if the particle size becomes smaller than electron mean free path, is that that means that electron basically hits the boundary of the particle even before it hits other scattering mechanisms like impure. So even before the impurity scattering happens, it actually hits the boundary, right? And then boundary of the particle actually also acts as a scattering source. So what that means is that electron scattering, due to this electron scattering at the particle surface, your damping rate becomes actually increases, right? Increases compared to the normal case. So here, I think it'll be instructive to look at this relation. Like if you look at this relation, the line width. What I mean by line width is the width of the resonance peak, plasmon resonance peak, which tells you about the loss rate. Okay, so as you go to a larger and larger particle, like 80 nanometers and above, here even larger particles, the line width or loss rate of your localized plasmon resonance increases. Why? Because of radiative loss, right? As I said, as you go to a very, very large particle, then radiative loss comes into play, and then your loss, the overall loss, which is the sum of non-radiative and radiative loss, increases. But the thing is, as you make your particles smaller and smaller, it never monotonically decreases, but like as you go to a very, very small particle, your line width actually increases slightly. And this slight increase is due to the fact that the particle size becomes actually smaller than the electron mean free path, so that non-radiative decay rate increases due to the particle size. Okay, so that's why you have this type of a phenomena. And then if you go to a even smaller particle, like particle size of 1 nanometers, which is about a few atom big, then classical electromagnetic theory no longer holds. So you need to take into account the full quantum theory. Okay, so what we learned, like the quasi-static approximation, can only be applied, say, between 10 to 100 nanometer particle size, where most of the applications lies in this particle size. And another interesting question is, like if you think about, so again, alpha, the polarizability of a metallic nanoparticle is 3b times epsilon m plus 2 epsilon d, and then epsilon m, was it epsilon d minus epsilon m? Okay, epsilon m minus epsilon d. Anyway, epsilon m minus epsilon d. And then, so the question is, what happens if we have same size of a sphere filled with air, but now the surrounding is metal? Like what would be the condition? What would be the polarizability in this case, or condition for the plasmon resonance? Well, in this case, because we just flipped the materials from from metal to air and from air to metal, all we need to do is to switch epsilon m and epsilon d, the position of epsilon m and epsilon d, in order to get the localized plasmon resonance in this case. And that's this. And in here again, if we have a void or cavity instead of sphere, then what we need to do is to switch the position of epsilon m and epsilon d, because here it's what's exactly happened. So if in this case, the resonance frequency increases right? Because this condition factor 2 is now in front of epsilon m. So it's the resonance condition is shifted. And from these two relations, we can also know what's going to happen if we have a metallic shell instead of like, like a field sphere or just a hollow spherical cavity. So if you have a metallic nanoshell, two possibilities of charge configuration is possible. So you have negative charges, and then here you have positive, so negative, positive, and then inside positive, negative. So it's like minus, plus, minus, plus. And this state is called anti-bonding state. And then there's another configuration possible, is that a minus, minus, plus, plus. So this entire thing becomes minus, this entire thing becomes plus. This is called bonding state. And of course, bonding state has lower energy, it's more stable. So it has a lower resonance frequency compared to the anti-bonding state. This is just to give you the full details of everything. And then if you look at a real particle plasmonics, it's actually, as I said, depending on the size and the shape of a metallic nanoparticles, it has many different colors. So you can see here, red, and then there's also green, yellow, and all colors are possible depending on the size and the shape of the metallic nanoparticle. And by using that, you can create a kind of what is called stained glass. So this glass, each pieces of glass has small metallic nanoparticles so that they have their specific color. And I already talked about this. So this is, again, is called Lycurgus cup. It's a Roman artifact at 4th century. And here, if you take the piece of cup and that piece of the glass, and then you look it in the TEM, you can see that this glass contains AgAu alloy nanoparticle of the size of about 50 nanometers. And because of this nanoparticle, this glass actually has maximum scattering and maximum absorption also in green, okay? So that if your light is from outside and then you are just looking at the scattered light, like in this, like in the case in the left, you look at basically the green color, because the green is most scattered color. And then if you look at, if you have your light source inside or behind the cup, and then see the transmitted light, then you see basically 1 minus green, which is a red, basically. Okay. So, and this is because this metallic nanoparticle has maximum absorption cross section also in the green color. Okay, so absorption is maximum in the green color, scattering also maximum in the green color, and that's why we have strange color, the dependence of this color. And so from now on, I'd like to talk a little bit more about the applications of metallic nanoparticles, or like a plasmonic localized plasmon resonances. And this is a really important paper back in this time, 2006. So this paper is talking about a fluorescence enhancement. So probably every one of you knows about what is fluorescence. Fluorescence is like this. If you have an electronic energy state here and here, and due to the vibrational energy state, electronic energy state basically the energy state can be divided into like multiple subbands. And then if an incident light coming in, then these electrons in the ground state hops to the high energy state. And then, and from here, electrons undergoes basically the scattering with phonons, and then they have their its energy becomes lower and lower and lower. Okay, and then from here to, I don't know, certain band in the bottom, it undergoes another energy transition, and then and then this transition is radiative, and this transition is called fluorescence, right? So that the energy of excited light and the energy of fluorescence light are typically different, right? See, the omega fluorescence is typically lower than the omega excitation, right? So this is how fluorescence occurs. And what people figured out, I mean, this fluorescence is extremely important in imaging applications, like especially in bio imaging field. This fluorescence is very, very important. And what people realized was that if you have a metallic structure close to a fluorescent molecule, so this, let's say this is a fluorescent molecule having this electric energy state, then compared to the same fluorescent molecule in the free space, sometimes this configuration gives you much better fluorescence yield, like fluorescence intensity, and sometimes this case gives you poor fluorescence intensity compared to the case of the free space. So people got confused, like what determines, because people did many experiments, and then in some experiments report, okay, fluorescence intensity increases if the fluorescent molecule is placed close to the metallic particle, and for the other cases, they report if the fluorescence molecule is close to the metallic nanoparticle, then fluorescence actually is suppressed. So people didn't know what is exactly happening until this point. And then this paper basically explains why in some cases you get a fluorescence enhancement, and in some other cases you get a fluorescence quenching. So that this paper is basically cited by a lot. I guess this cited by more than 4,000 times. So the idea is simple. So the fluorescence rate is determined by two things. One is the excitation rate. So the rate of this exciting process, excitation process. And then second thing is called quantum efficiency. So quantum efficiency is like the total decay rate. So the radiative plus non-radiative decay rate, which the sum of them gives you the total decay rate. And then here it's the radiative decay rate. So here's the thing. So this equation is very intuitive. Like excitation rate, of course, determines how much of electrons will be excited to the higher energy state. And then this quantum efficiency gives you, internal quantum efficiency gives you how much of this transition will become radiative, right? So if this factor is much smaller than 1, which means non-radiative decay rate is much stronger than the radiative decay rate. Even though this transition happens, there's no radiation out, right? So in order to get a better basically fluorescence enhancement, we need first to excite, to enhance the excitation rate, and also making this quantum efficiency as high as possible. Okay, and then excitation rate is proportional to the dipole moment of the particle times the electric field at the position of the particle. So it's P dot E squared. Okay, so if you draw the excitation rate here as a function of distance between the particle and the fluorescent molecule, it just increases monotonically as the distance between the particle and the molecule becomes closer, right? Because near the particle, electric field is stronger due to the plasmon resonance, so that if you make this particle closer to the molecule, excitation becomes stronger. It's always the case. And the problem is that as your particle becomes closer to the molecule, the non-radiative decay channel, which is called like Forster energy transfer. I don't want to go into detail, but it's like a dipole-dipole energy transfer, non-radiative energy transfer, also increases. Okay, and because of that increase, as you go to as the distance between the particle and molecule smaller, the quantum yield or quantum efficiency actually vanishes, because non-radiative decay rate increases too much, so that this entire term becomes zero. So if you draw these two tendencies, the excitation rate increases monotonically, like in red curve, and the quantum yield decreases monotonically, like in this blue curve. So if you multiply this, you get this curve, right? So peaks at a specific distance, and then decreases as you move away from that distance. So that if you are not careful in terms of making the distance between the particle and the molecule to be exact, then in some experiment you are in this regime where most of the energy is just quenched, just go to the non-radiative decay channel, so that you cannot see any fluorescence. So then if you are in this regime, you might say that, oh, my fluorescence has been suppressed. But if you're in this regime, where the distance between the particle and the molecule are not that much different compared to this regime, but here you get a significant increase, right? And you report an enhancement. So this mechanism has been figured out by this guy, Novotny, and then this paper got a lot of attention at that time when it was first published. Yeah, so and another usage of this localized surface plasmon resonance is a surface enhanced Raman scattering, or also known as SERS, right? So surface Raman scattering is like in this process, like you have you excite your electron to a virtual energy state, and then this energy, this electron going back to not to its original position, but in a little different position, so that you have a Raman scattering. And then the energy difference between the ground state and this state is determined by phonon state. Okay, and then here you can see that both the excitation process and the extraction process can be amplified by the high electric field strengths. As I said earlier, P dot E squared basically determines the the rate of excitation and the going back to ground state transition, so that the Raman scattering process can be enhanced by the factor of e to the power of force, or in other words, like the square of the intensity. So if your plasmonic nanoparticles makes a strong plasmon resonance that have a high electric field compared to the free space, then your Raman scattering process will be amplified or enhanced by factor of like e to the force. Right. And another application that people were interested about was energy applications. Like previously in thin film solar cells, because the active material was kind of too thin, so that most of the light is not properly absorbed in the material, but just reflected back or transmitted. Okay, so you lose basically most of light energy due to the reflection or transmission. So in order to overcome that constraint, what people did was people place a small metallic nanoparticles inside or above the thin film solar cell. And because these small nanoparticles can hold a plasmon resonance, so that light has basically longer chance to be absorbed in the active material, so that the overall absorption increases and overall efficiency increases. And this one is one example. Like compared to a flat solar cell, this is a JV curve, like a current and voltage curve of a solar cell. Compared to the flat solar cell, which doesn't have any metallic structure, if you have a nanoparticle cluster or this three-dimensional strange looking nanoflower structure, you can have much higher performance, much higher kind of light conversion efficiency, because due to a higher absorption of incident light. Yeah. So I'm just keep talking to you about the applications. Another application is sensing. As I said, metallic, these plasmonic resonance is very sensitive, so that like the resonance, if you have two nanoparticles separated by a small distance, then the overall resonance of these two particles changes by a lot if you change the distance between the nanoparticle. Okay, so what people try to show here is that they have two nanoparticles attached by a DNA, and if this DNA is double strand, then double strand DNA is stiffer than single strand DNA. So if this becomes a single strand DNA, it's less stiffer, so the distance between the nanoparticles become closer. And then if it's a double strand, it's stiffer, so the distance between the nanoparticles are larger. And depending on this this double or single strand, you can actually see the spectral shift of a scattering signal, right? And then this can be used actually in the other way around. Basically, by measuring the spectral shift, you can actually guess the distance between the metallic nanoparticles, and people call this as a plasmonic ruler, because you can measure a very, very small distance by just checking their absorption or scattering spectra. And also the molecular sensing, as I said, it's pretty similar. It's just the same as the source. And you can see here, compared to the case with a flat gold, if you have a structured nanostructure which can support plasmon resonance, your source signal, your Raman signal increases by a factor of like maximum 10 to the 6, like 1 million times larger than the flat case, so that you can reach to the single molecule detection sensitivity. Okay, so this is basically all for the localized plasmon resonance.